My name is Spencer Van Koevering, and this summer I worked on control barrier functions. Now, control barrier functions are a way to provide analytically provable safety guarantees to a control system. And so we can define our safe set based on some function, and we can derive a constraint from that such that if our input satisfies that constraint, then we are guaranteed to remain in the safe set as long as we started there, or to converge to it if we weren't already in it. And that's called set invariance. It's a very strong property. However, if we can't find a feasible solution, if we can't satisfy these constraints, then behavior becomes unpredictable. We don't really know what to do. And so it's important to be able to find feasible solutions to these things. And there's a paper published recently from the Argo AI Center where there was a feasibility guarantee. The paper is able to guarantee that if a feasible solution to its barrier exists, we will find it. And that's a very strong condition. In addition, that paper also proposed a framework for being able to guarantee safety up to a confidence level under uncertainty, which is also really nice because in the real world, uncertainty exists, and we can't just naively use a deterministic function to guarantee safety. However, these solutions only apply to barriers of degree 1. And barriers of degree 1 are not all barriers. And in fact, there are barriers of degree 2 we would like to use this on, especially for car models. So my work this summer was to extend these guarantees to a degree 2 control system, specifically a car model, which we will use and demonstrate for a lane changing scenario. So the technical objectives are to be provably safe under uncertainty to a degree of confidence, and to guarantee that if a feasible solution to our problem, to our constraints exist, that we will find it. So this is our scenario. We are the ego vehicle. There are 3 other vehicles we're tracking in front of us and behind us in our current lane and our target lane. And I'm defining our safe set there using the function h. And the idea is we want to keep h large enough that we don't hit the car in front of us or the car behind us. We'll have one of them for each other car. Now these are our system dynamics. Don't worry too much about specifics. We have to have these in order to do barrier function analysis. But this is how we're assuming cars behave. And you can see epsilon 1 here is bringing in our randomness to our x position. Beta is kind of steering angle. It's not exactly, but it's interchangeable. And a is acceleration. Now, a control barrier function, strictly defined, is our function h. And then from it, we derive the constraint that defines set B, where as long as u is in set B, then the safe set will be invariant. And so the barrier we'd like to use is this h of x is equal to xe minus xm squared minus r squared, where xe and xm are our centers of mass, the positions in x, and r is some additional distance to count for the lengths of the vehicles and a little bit of extra distance, just for safety's sake. The downside is that a first derivative of this function isn't going to get us acceleration. We need 2 derivatives to do that. And if we don't have acceleration in our constraint, then the only input that's going to be affected by it is our steering angle. So the only way you could avoid hitting the car in front of you is by swerving and not actually slowing down. And that's not a very desirable way to drive. So we need a new approach. And there's already a way to do this, and that's called an exponential barrier function, which is basically the same thing as a control barrier function, but it works on barriers of higher relative degree greater than 1. And so the constraint looks pretty similar. It's this double derivative of h plus the alpha 1 h plus alpha 2 h dot, where alpha 1 and alpha 2 are constants that have some constraints on them themselves. And so our barrier is going to look like for each other vehicle this term here, where the probability that we satisfy that same constraint is greater than or equal to some arbitrary confidence level eta. And we can choose gamma to some extent. And so what we're going to do at each time step is optimize gamma to make this constraint as easy to satisfy as possible. And so by doing that, we guarantee that if there is a solution for any gamma, we will find it, which is the same guarantee we had in the degree 1 case. Now this does end up being a little messy. The numbers don't pan out quite as nicely as in the degree 1 case, but the technique still works. So we implement this new barrier into an existing scenario, and we test it against itself with the probabilistic barrier interchangeable with deterministic, and the gamma optimization on and off, as well as comparing it with an existing first degree barrier that's kind of physics-based to get around the degree 2 problem to see how we perform. So you can see that our probabilistic barrier with optimization performs very nicely, better than all of the other barriers with one of these features off. Our collision rate is comparable to the existing degree 1 control method, and we are much, much more feasible. And that's great. We're doing well in comparison. And here is how long it took to complete the lane change. And you can see that switching to a probabilistic barrier actually made the lane change faster. And then K-alpha optimization, or excuse me, gamma optimization, also increased our ability to finish lane changes efficiently. Thank you for your time. Here are my references.